I want you to imagine just for a second the sheer volume of energy you consume over the course of a single year.
Oh, it's a lot. Most people don't even realize.
Right. I mean, think about the daily commute, the constant hum of your refrigerator, the air conditioning running all summer.
The hot water heating.
Exactly, the hot water heater. And, the power feeding the very device you're using to listen to me right now. If
Mhm.
you were to add up the physical footprint of all that energy, you might picture like a literal mountain of coal or thousands of gallons of gasoline.
Which is a massive environmental footprint.
Massive. But now I want you to imagine powering that exact same lifestyle, everything you do, 24 hours a day for an entire year, and producing a total amount of physical waste that weighs the same as a single sheet of printer paper.
Wow.
Roughly 5 grams. That is the fundamental premise we are exploring today. Welcome to the deep dive.
It really is a profound visualization. I mean, when you frame a year of modern human existence against, 5 grams of byproduct?
Yeah, just 5 grams.
It completely reorients how we think about energy density and, obviously, environmental impact.
And to figure out if that 5-gram reality is actually our impending future, or just, an incredibly well-funded piece of science fiction, we've pulled together a really comprehensive stack of sources today.
We have some heavy hitters for this one.
We really do. We're looking at official technical material from the Department of Energy, engineering breakdowns from the World Nuclear Association,
Right?
and a highly pragmatic, honestly deeply realist report from the Information Technology and Innovation Foundation, the ITIF.
That ITIF report is fantastic, by the way.
Yeah.
Very grounded.
It is. So our mission today is to cut through all the venture capital hype and understand the reality of small modular reactors, or SMRs.
Because there is a lot of hype right now.
So much hype. We want to know if SMRs are the genuine mechanism for a clean energy future, or just, a colossal misallocation of resources.
Yeah.
And as a quick constraint check for you listening, this is a deep dive. We are here to synthesize the underlying physics, the brutally complex economics, and the geopolitical realities buried in these sources.
It's not just a surface-level skim.
Right. Okay, let's unpack this. Where is the logical starting line for a topic with, frankly, this much historical baggage?
Well, I think the only place to start is with the economic reality that governs global energy. The ITIF report frames this around a concept called price-performance parity, or P3.
P3. Okay, break that down for me.
So if we want to understand SMRs, we have to strip away all the environmental idealism for a moment and just look at the raw math.
Right.
The reality of climate change is that regional solutions are meaningless. Solutions only work if they scale globally.
Right, because emissions are a global problem.
Exactly. And developing countries that are rapidly industrializing, lifting billions out of poverty, they cannot and will not pay what people call a green premium.
I mean, they aren't going to deliberately stunt their own economic growth by purchasing expensive, nascent, clean technology when, cheap coal and natural gas are just sitting right there.
Precisely the point the ITIF makes. For nuclear power, or honestly any zero-carbon technology, to genuinely displace fossil fuels globally, it can't rely on subsidies forever.
It has to stand on its own 2 feet.
Right. It must independently reach P3. It has to become objectively cheaper and better than burning coal. If a technology does not have a mathematically sound, rigorously vetted pathway to reaching price-performance parity,
then building it is just an expensive academic exercise.
Exactly. Just an experiment.
So the entire push to take traditional, sprawling nuclear power plants and shrink them down into small modular reactors, that's fundamentally an economic maneuver.
Yes.
It's an attempt to redesign the manufacturing process to hit that P3 target.
That's the core of it, yeah.
But I think before we get into the assembly lines and the economics of shrinking a reactor, we really need to establish a baseline of what is actually happening inside the core.
Always a good idea to understand the physics first.
Yeah, and the Department of Energy sources provide a really stark contrast between fission and fusion. And I want to spend some time here because, these two terms get conflated constantly in public discourse.
They do, all the time. And they represent completely opposite approaches to extracting energy from the fundamental building blocks of the universe.
So let's look at fusion first.
Okay, fusion.
Fusion is the mechanism that powers the sun, right, and every other star. The concept is that you take 2 very light atoms, usually isotopes of hydrogen, and you force them together.
You slam them to each other.
Right. You slam them together with so much kinetic energy that they overcome their natural magnetic repulsion and fuse into a single heavier atom, like helium.
And that process of fusing, releases an absolutely staggering amount of energy.
I mean, we're talking star power.
Literally, the energy yield is immense, significantly higher than what we currently achieve with our commercial reactors. And the byproduct is essentially benign.
Meaning no highly radioactive waste.
Right. You aren't left with long-lived, highly radioactive spent fuel. It is, by all theoretical measures, the ultimate energy source.
Okay, wait. If fusion is the holy grail,
Yeah.
if it gives us vastly more power and essentially zero radioactive waste, why are we spending billions of dollars and, the next hour of our time talking about fission today?
It's a fair question.
Shouldn't every single cent of our energy budget be poured into fusion research?
Well, it comes down to a matter of physics, engineering timelines, and the immediate demands of the global grid. To force those hydrogen atoms to fuse, you need to recreate the conditions found in the core of a star.
Which I imagine is not easy to do in a lab in, Ohio.
No, it's incredibly difficult. You need millions of degrees of heat and immense gravitational pressure. Recreating and, more importantly, sustaining that kind of plasma state on Earth requires incredibly complex magnetic confinement fields, or high-powered lasers.
So it takes a massive amount of energy just to start the reaction in the first place.
Exactly. And while we have seen recent laboratory breakthroughs where a fusion reaction produced slightly more energy than it consumed.
Well, it was huge news, yeah.
It was huge. But creating a stable commercial fusion power plant that can reliably feed the grid, that is likely decades away.
Yeah.
We are facing an immediate compounding crisis of surging electricity demand and the need for rapid decarbonization right now.
We don't have 30 years to wait for a miracle.
We do not.
We have to play the hand we are dealt today. Which brings us to fission. If fusion is slamming small atoms together, fission is tearing massive atoms apart.
Correct. Fission is the established technology. It powers every single nuclear plant operating on Earth today. Instead of light hydrogen, you start with a heavy, unstable element, typically an isotope of uranium, like uranium-235.
Okay.
You fire a single uncharged particle, a neutron, at the nucleus of that uranium atom.
And the nucleus absorbs the neutron, becomes critically unstable, and violently splits into two smaller atoms.
And in that exact moment of splitting, a tremendous amount of binding energy is released, primarily in the form of kinetic energy, which we experience as intense heat.
Right.
But crucially, when that uranium atom splits, it also ejects 2 or 3 additional loose neutrons.
Ah, and those newly freed neutrons go flying outward and crash into neighboring uranium atoms, cause them to split.
Which releases more heat and more neutrons.
Cascading outward. The chain reaction.
Exactly. That chain reaction is the engine. And the World Nuclear Association source provides a very grounding way to think about what we do with that engine. Once you strip away all the complex quantum mechanics, a nuclear reactor is fundamentally just a very large, incredibly sophisticated tea kettle.
I have to admit, I love the world's most complicated tea kettle analogy.
It's accurate.
It really takes this terrifyingly abstract concept of atomic decay and grounds it in everyday physics. You're splitting atoms to generate mind-boggling amounts of heat inside the reactor core. And what do you do with that heat? You boil water.
That's it. The heat from the fission reaction is transferred to a circulating coolant. In most current designs, that coolant is highly pressurized water. That water gets intensely hot and is used to boil a secondary loop of water, turning it into high-pressure steam.
And then that steam is directed through massive pipes to forcefully spin the blades of a turbine.
Which turns a generator, and the generator pushes electrons onto the grid.
It's literally the exact same mechanical process as a coal plant or a natural gas plant.
Exactly the same.
You're just replacing fire with splitting atoms. But obviously, you can't just let an atomic chain reaction run completely unchecked.
No, that would be bad.
Right, because the heat compounds exponentially, the water boils off, and the physical metal of your tea kettle melts down into slag. You have to control the rate of the fission.
Yes.
The WNA documentation mentions the use of control rods, specifically highlighting materials like silver and boron. I understand they act as brakes, but how do silver and boron actually stop an atomic reaction?
It all comes down to a property called the neutron cross-section. Materials like silver, boron, and cadmium have an incredibly high probability of capturing a free neutron without undergoing fission themselves.
Oh, interesting.
Yeah, you could visualize these control rods as atomic sponges.
Okay, so if the reactor operators see that the temperature is climbing too high or the chain reaction is accelerating too quickly, they physically lower these boron and silver rods down into the uranium core.
Exactly. As the rods descend into the core, they sit right between the uranium fuel assemblies. So the stray neutrons that are flying around bounce into the control rods and are absorbed.
And because those neutrons are soaked up, they can't hit the next uranium atom.
Right, the chain reaction is throttled. And if you want to increase the power output, you just slowly withdraw the rods, allowing more neutrons to find their targets.
It's a highly precise mechanical method of regulating the atomic physics.
It's very elegant when you think about it.
When you break it down like that, yeah, the mechanics are surprisingly elegant. But what truly separates this from burning coal or gas is the energy density.
Oh, the density is incredible.
The sources emphasize this point heavily. A single pellet of enriched uranium fuel, roughly the size of a sugar cube or like the tip of your finger.
Just a tiny cylinder.
Yeah, that tiny cylinder contains the equivalent energy of 1 full ton of coal.
Or roughly 149 gallons of oil. Or 17,000 cubic feet of natural gas.
That is insane.
The density is almost difficult to fully comprehend.
A sugar cube versus a literal mountain of black rock. And that density is why these plants are capable of running at 100% capacity 24 hours a day, 7 days a week, for 18 to 24 months straight without ever needing to shut down to refuel.
Exactly.
It doesn't matter if it's the dead of winter, if a hurricane is blocking the sun, or if the wind has died down. The grid gets a constant, unwavering baseline of power.
And that reliability is the defining characteristic of nuclear baseload power.
But I'm looking at these facts, and I'm looking at the real world, and I'm struggling to reconcile the two.
How so?
Well, if fission works so reliably, and if the fuel density is mathematically superior to anything else we have, and if it produces 0 carbon emissions during operation, why has the nuclear industry effectively been frozen in amber in the West for the last 40 years?
It's the multi-billion-dollar question.
Right. Why aren't we just building these giant, reliable tea kettles outside of every major city?
To understand the stagnation, we have to examine the systemic failure of the giant reactor model. Building a traditional, large-scale gigawatt nuclear power plant has evolved into an almost insurmountable financial and logistical nightmare.
The ITIF report spends a lot of time dissecting this. They point to the Vogel plant in Georgia as the prime example.
Plant Vogel, yes.
Plant Vogel was supposed to herald the great American nuclear renaissance. It was the first new nuclear construction approved in the United States in decades. But instead of a triumph, it became this huge cautionary tale of mega project economics.
It really did.
It arrived roughly 7 years behind schedule, and the budget swelled to over $30 billion, massively over initial estimates. The ratepayers in Georgia are going to be shouldering that debt for a generation.
And this paralysis is not confined to the United States. The ITIF also highlights the Sizewell C project in the United Kingdom.
Oh, right.
The initial cost estimates for that facility were around £16 billion. The most recent projections suggest the final cost could balloon to £40 billion.
40 billion pounds. We are talking about nearly 50 billion US dollars for a single power plant.
It's staggering.
That entirely breaks the price-performance parity model we established at the beginning. No developing nation is going to sign a $50 billion check for one power plant. How does a construction project miss its budget by tens of billions of dollars? What is fundamentally broken in the process?
The root of the dysfunction is what economists call the bespoke project mentality.
Bespoke, like a custom suit.
Exactly. When a utility decides to build a 1,200 megawatt nuclear plant, they aren't buying a product off a shelf. They are initiating a generational infrastructure project. Every single site is unique.
Right, because the geography is different everywhere.
Yes. The seismic profile of the bedrock requires custom foundation engineering. The hydrology of the local river or ocean dictates a custom cooling system design.
So every single plant is essentially a one-off prototype.
Furthermore, because the West largely stopped building nuclear plants in the 80s and 90s, the specialized supply chains atrophied.
We just forgot how to do it.
Essentially, yes. The workforce, the highly skilled laborers who know how to pour nuclear-grade concrete without voids, or forge massive steel pressure vessels, or perform X-ray inspected pipe welds, they aged out of the industry. Or they moved to other sectors.
Oh, wow.
So when a project like Vogel begins, the contractors are essentially training a massive green workforce on the job.
I keep thinking of the analogy of building a house. If you need shelter, the rational economic choice is to buy a prefabricated home. Or hire a developer who builds a standardized model in a subdivision where the crews know exactly where every pipe and wire goes because they've built it 50 times before.
That's standard manufacturing logic.
But the